Hi, you're very welcome back to clip 2 on wind power. And we're going to have a look at the attributes or the characteristics of wind power. And when I was in my early teens, I resurrected a wind charger that my father had during the war. He took it down when the mains power came, and being young and inquisitive, along with some friends, we built a hut out in the back garden, and we had two options to choose from. This was a shortened version, about 5 feet long or a little less, of what was known as a wind turbine blade at that time. And it drove a direct current dynamo, which is quite a little bear in itself. And this little device here is to stop the current flowing in reverse. In other words, to stop the battery to which this was attached driving the turbine or propeller when the wind died down. But we didn't do anything by half, and so this was the mainstay of the turbine. This is about standing 7.5 feet easily, 2 meters plus. And you can see the way it's designed. It has a beveled cutting, and that gets less out towards the end because the end travels faster than the center. So this would revolve at an unbelievably high speed, and we always had to be careful. If this hit you in the head, you were gone. Now this was mounted on a dynamo, the same as the other one. It's a bear, and this was a specially wound Dodge dynamo, and you could actually make it produce power by hand. It's still quite a heft. And I put that on the top of an ash tree when I got my parents away one day, and I don't know how I survived. Just good luck, I think. And we had it running anyway, but it taught us a lot, and I began to discover that when the wind wouldn't blow, we'd be in darkness, and when the wind blew, well, it would blow the bulbs. So a battery was duly fitted. That helped a little, but only a little. So we're going to look at the attributes of wind energy now. And the first thing we hear from the wind industry is that Ireland has the best wind speeds in Europe. Well, in actual fact, Ireland's wind speeds are divided in three. Basically, the west coast up to North Antrim, the Midlands, where we are here, and let's say Wexford and Wicklow here. And that equates, we say, Wexford to London, the Midlands to Lower England, and the west coast to Scotland. All of Scotland, all of England, all of Britain, north of Hull, including all of Scotland, has equal and better wind speeds than the best wind speeds in Ireland. Now, if we look at a rough map of Europe, poor artwork I admit, Ireland's about 1/5 of the area from the southern tip of Spain right up to the habitable area of Norway and Sweden. So we've about 1/5 of it, and the best wind speeds are the more further northerly you go. So while Ireland has good wind speeds, it's not the best. This is just more of the spin that we get from the industry. Now, if we look at wind turbines, a wind turbine generator, it has a generator the same as mains electricity or a power station. And it starts to generate at about 12.5 miles per hour wind. It must be shut down above about 37 miles per hour. Now remember, it could possibly go up to 43 or 4, but the damage is done if you allow that, so they have to shut it down before the top speed is reached. That's a range of 24.5 in which you can produce energy, and 33 miles an hour is its top ideal speed of wind. Now the industry were giving a load factor, which we've already seen, of 35%. In other words, you'd get 35% of the rated output of the turbine over a year due to variations in wind. But that was reduced to 30.5 because I questioned it and I produced facts to show that was wrong, and EirGrid reduced that down. And it now stands at 23.5 for 2010, which is much more realistic. In northern Scotland, in 6 months in 2010, it was 17.5. So we see there that a turbine starts at 12.5 miles per hour wind Ideal is 33 miles per hour, and the stop, it must be shut down at about 36, 37. This can vary, but if you make this bigger, greater, higher, you have to make this higher also. In other words, a very delicate turbine that would cut in at 8 miles an hour would not be fit to withstand very high winds. So this is the general run of them. So I carried out my own study here at Kingsford based on the Beaufort scale and a small measuring device, a little alternator where I could measure the hertz of it, and I was able to deduce that our wind speeds around Clonus and South Ulster, North Leinster, on the higher ground where I live, is 24.1%. And that is exactly in line with Met Éireann's 30-year record for wind speeds at Clonus from 1971 to 2001. That matches that. The Digest of UK Energy Supplies in 2007 gave onshore turbines in Britain with a load factor of 27.5, and offshore 25.4, an average of 26.4, slightly better than my figures for that year, which was slightly windier. So this thing of load factor of 35 would still be there were it not for people like myself who called them to task and made them show their evidence, and they couldn't. So we look at load factor. That's load factor. It's just a bit cut out there. You know what that means. At 24.5%. That means that for the red area you have good full output on this pie chart. On the green area you have some marginal output. Very doubtful if it has much addition to switching off power. This would probably allow you to shut off conventional plant. This probably might not. Doubtful. But all this area here, there's no power at all over a year. Now the original figures by EirGrid and by the wind industry is 35% load factor, which would only increase that to there. So this shows you that we're being spun a yarn, and we're being spun a yarn on this. And you can know this yourself. How many calm days are there? Now bear in mind, this bears another factor impinges on this, and that's the consistency of the wind, which is the main problem with it. Another thing you frequently read in the paper is that a certain wind farm will power a lot of homes, and the London array with 317 projected turbines was said to power 1/4 of London. That is utter nonsense. I did my own statistics, and it's a bit complicated, but it's based on the load factor, their figures, and it's even overstated. And they take the consumption of homes at the lowest point in the day at 3 o'clock in the morning. On average, one turbine in average wind speeds will power 31 homes at periods of peak demand. And that is subjective too, but it's much more realistic. That's based on the load factor. So again, a total overstating of the usefulness of wind power. One very important factor in considering wind power is what's called wind penetration. And how much wind can you actually let into the system? Some within the industry and some in the energy regulator and EirGrid and the Department of Energy will tell us there are times when they get 50% penetration. The problem with that, it's often accompanied by future days when they have very near blackouts as a result. The more wind you let in, the more difficult it is to control it and keep it stable. So what is the amount of wind penetration? What's the maximum that can be let into the system? And my figures are about 22% on average. This can vary a bit, but there's a very important point to this. The amount you can let into the system, even if you put it at 26 or 27%, depends on the amount of demand. So we'll say at 22%, but demand is full, you can have 22% of the power being generated in Ireland from wind. If demand goes down to 3/4, then you can only have 3/4 of 22% from wind. If demand goes down to half, you can only have 11% of your power from wind. And if demand goes down to 1/4, you can only have 5.5% of your power from wind. So if the wind is blowing continuously through a 24-hour period, there are many times when you cannot even use a lot of it. It's constrained off. Now, reason why you can't allow it in is because, number one, it's inertia. If it was allowed in big amounts and slow demand, would control the whole system. It would make it very difficult to run a conventional plant. And the increase and decrease in voltage is hard to control, and therefore you have to keep it down. Now, this is being denied, and this is why me and myself and my association, we want this properly inquired into. But in the absence of that, we would say that the first country to exceed 22% of wind power, and that doesn't appear to have happened anywhere yet, will soon discover that they're limited in the amount of that wind they can let in. And it stands to reason. Why don't we have countries with 100% of their generating capacity for wind? We don't have it anywhere. So surplus wind generation is constrained off, but it's paid for in full by you. I've explained that in the section on how it's paid for. And wind now is 21% total nameplate value in Ireland, 21% of the system, and that's set to double over the next 10 or 15 years. So the more and more wind power we put into the system, the less and less of it we can actually use. And this idea that you can use raw wind power and turn off all your other plant, that is a complete fabrication. So now we're going to look at why it is limited in what you can feed it, and what are its limiting factors. And one is it's non-dispatchable. This is provided from the regulations. You don't know if you'll have it next Thursday at 4 o'clock, even no matter how you plan. It has an inadequate load factor of about 25% overall over the whole world, and that load factor is forced. So if your car is unavailable for a certain time, but it's there when you need it, that's okay. But if you go out in the morning when you want to get to work and it won't start, that's a forced shutdown. So the wind load factor, unlike other forms of plant, is forced. It has no correlation between supply and demand. The wind can be blowing at 6 o'clock on a public holiday Monday morning when nobody wants power. There's no correlation there at all. It's erratic gusting nature. Now this can be evened out a little by spreading our wind turbines out over the country, because a gust may come in Cork at a different time than it may in Cavan. But this is only minor. It's only a minor adjustment that can be done with this. There's no way of knowing if it will turn into a gale. The wind industry continually talk about forecasting. They can read the forecast. If you do your own tests on the wind forecast, just watch the weather forecast and see how accurate it works, and see how many times throughout a 24-hour period it turns from good wind to calm. You'll get the idea that it's not consistent, and therefore you cannot turn off plant. There's no way of knowing if high winds will turn into a gale. I have that. And this is nationwide. So if you have really good winds tonight and you've turned off your plant, and the next thing it turns into a gale, you have a blackout. And because of that, they are going over more and more and investing into open cycle gas turbines, which can be brought online real fast, and they're more inefficient and more costly. Now, the long anti-cyclone weather patterns all over Europe. Our long winters are proof of that, and you get it in the summer. If you have calm conditions in Ireland, you generally have them in Scotland and in Denmark and many other places. The wind energy cannot be used raw. It's limited penetration to the grid. There's a limit to the amount of it you can put into the grid. It cannot be stored. We're dealing with that separately. And the output variation is huge. If you take the size of two turbines, the small and the big, what's the difference in the two? Well, it's the very same as if you had a back garden which is 25 square meters and you had to dig it. And suddenly that was increased by doubling one of the sides, doubling both of the dimensions. You'd now have a factor of 4. You'd have 100 square meters to dig, 4 times the amount. So if you increase the size of the turbine, the output goes up 4 times as you double the size of the turbine. So here's an example here of a 5-meter diameter turbine. It's doubled to 10 meters. At 5 meters you get 20, the area swept, and the output of it is, let's say, 20 kilowatts. At the 10-meter diameter, that goes up to 80 kilowatts, a factor of 4. So it applies to all turbines. Double the diameter of the turbine, the output goes up by a factor of 4. Now, what about wind speed? Now, this here relates to wind speed. This is different to the diameter of the turbine, and it goes up by the cube. And if you take a tank 5 by 5 by 5, so that's a square tank there, small tank, and you double the size and double it here, that goes up by the cube. So if we look at that, 5 by 5 by 5 is 125. Whereas if you double it to 10 by 10 by 10, it's 1,000. It goes up by 8. It changes from 125 to 8. So double the wind speed and the output goes up by a multiple of 8. Okay, that's different to the blade, and this is really more important. So the changes in wind speed are not linear. They're much more erratic and much more multiplied. So if we look at here is a big turbine, 22.5 meters in diameter. It gives out 500 kilowatts at a particular time and a particular wind speed. At the same wind speed, a 45 meter diameter one, double its size, gives out 2,000 kilowatts. That's based on size, a factor of 4. In a 15 miles an hour wind, you'll get, in the wind speed, you'll get 60 kilowatts. At 30, you'll get 483 kilowatts. At 22.5, you'll get 204 kilowatts. So it goes up by a factor of 8. It goes up in a much greater amount. So by doubling your wind speed, the output goes up by 8 times that. Now, one of the problems with this is that you need cabling to match this. Now, at a wind speed of 19 miles an hour, you would need a cable of about 10 square meters. Where at 38 miles an hour, you'd need a cable of about 38. At 38 miles an hour, you'd need 10 by 10 by 10, a factor of 8. You'd need 80. So, whereas for 19 miles an hour, you might need that size. For 38 miles an hour, you'd need it bigger. You'd need it something that size. And this has a major implication for cabling. So we look at it that between cut-in speed at 12.5 and 19.9, roughly 20 miles an hour, that happens 22% of the time, or 80 days a year. So the bulk of the wind generation period is just low, under 20 miles an hour. From 20 to 24, it only happens 5% of the time, 19 days a year. And from 24 to 30, it only happens 1.6% of the time, or 5.7 days a year. And then it goes marginally up at very small amounts. The bottom line is that you need 100 square meters cabling, or 11 millimeters diameter for the most of the wind. But you need 800 or 30 millimeter diameter for just these 28 days. So we just see it here. So at wind speeds of 15 to 30, output goes up from 60 to 483 kilowatts. And the cabling needed in diameter goes up from 11 millimeters, roughly about that, to 30 millimeters, which is roughly that. And that's a colossal difference and a colossal expense. And that improvement, that bigger cabling, is only for 28 days of the year. And the expense of that is massive. Now, on a typical day, this says here, typical day, sorry you can't see it, you and I are running the grid. We can have a good idea of what the forecast demand will be. So it'll be a certain amount. It's roughly the same every day. So what can we shut down? Will wind turn calm? Will it turn into a gale? This will a lot depend on how much wind we have. If we only have a few windmills, well, we can probably cover it with the capacity reserve. If we have a lot of windmills, you can't cover it with the capacity reserve. And a big issue here would be, how important is it that we keep supply going? And experience is that very, very little of this can be shut down. The wind industry and all the people involved in wind generation, they want to deny this. They do not want to measure wind power on what you can shut down. Now in Germany, they were all starry-eyed about this, but they weren't getting the results. And they commissioned a report in 2005. And that report stated that for every 48,000 megawatts of wind, only 28,000 megawatts of conventional plant could be shut down. Sorry, for every 48,000 megawatts of wind, only 2,000 megawatts of ordinary power could be shut down. So they couldn't believe this. This is only about 4%. So they commissioned a second report because they didn't believe it. And the second report confirmed the first report. This is the pure hard facts. It mightn't be very popular. This is E.ON in Germany, a major supplier of power in the Saxony area, Holstein Saxony area of Germany. So imagine that, 48,000 megawatts of wind power. You can only shut down 2,000 megawatts of conventional plant, or 4%. And this has been proven. And in fact, it's even worse in many other areas. So if we convert those figures to Ireland, in Ireland we have, it works out with our penetration and our capacity credit as published here at about 8.3%, we can shut down 1.74%. I get 1.6 myself, but I'm going by the official figures. In Germany, 4% will give you 0.76% of plant. 8% in Germany would give you 1.52%. So Germany is going from 8% to 4%. The UK found in the digest of UK energy supplies that onshore allowed the shutting down of 1.1% and offshore 0.2%. Nearly nothing. I don't know why offshore. It's to do with salt building up on the blades and long periods of them being out for repairs. Now the Irish winter peak demand, and we're going to show it here. EirGrid publishes figures for the Irish winter peak demand over the last 10 years. And they're 2001 to 2009. So the Irish winter peak demand. And during that period, the actual amount of power produced in wind farms, the load factor, the actual production of power, was 1.6%. But if you base it on the amount being shut down, credit capacity, what it actually contributed, there was 1.3 parts of wind for every 998.7 parts of conventional power. Look at that. There was less than 2 parts per thousand of the actual contribution of wind per thousand over a 10-year period. Okay, that's in EirGrid's, you'll get that on the internet, EirGrid's adequacy report 2010 winter peak demand. Okay. So a big issue that I can't fathom out and can't get the proof of is that theoretically at small amounts of wind you could shut down over 10% of plant, but that falls rapidly as you increase the amount down to maybe 1 or 2%. Recent evidence is suggesting that in fact you can't shut it down in any case. I just don't know the answer to that. But we do know that as you increase up to 10 or 15% wind, it drops down to about less than 2%. The other scenario is that at low levels of wind you can shut down a good lot. But when you get over to a certain amount here, you actually need more fossil fuel, not less, to keep the wind going. And this was brought out in a representative of E.ON UK in 2008, published in the Guardian newspaper. And he said that if they rely on wind power, they're going to have to increase the conventional UK generating capacity from 76 gigawatts to 120 gigawatts. In other words, building more power stations. And that's precisely what's happening here. Now, UK Energy Research Centre stated that conventional plant will not be shut down during high wind. So this is the whole nub of my argument. You must value wind on what it can shut down. It's useless if you can't remove your reliance to some degree on fossil fuel and nuclear fuel. So moving away from now, one of the effects of this, in order to try and deal with the inconsistency of wind and the stopping and starting, they're moving away from the good old slow plant, which took 8 hours to start, to gas, to open cycle gas turbine, so that they can bring it on stream real quick. This open cycle gas is no more than 35% efficient. No more. Whereas this other one here could be up to 80-90% efficient. So we're losing efficiency. And this is so that they can say that wind is working. But you have to compare like with like. And Loon Common Offaly recently announced that they're going to build a gas turbine power station in County Offaly. But they're a windmill company. This is to back up their windmills, because the conventional generators won't take their power because it's too erratic. So they're going to build their own conventional plant. And there we are. We're increasing our ability to burn fossil fuel. In the London Array, Royal Dutch Shell said that they would come in for 40% of the investment cost to build 317 turbines in the Thames estuary. And when they went to sign the contract, they were told they'd have to build 2 coal-fired power stations on shore. 2 coal-fired power stations. They headed away. They wouldn't sign up to it, and it's still up in the air. So that shows you that you need conventional power when you have wind. It's a complete folly to think that it's going to shut down power. Now, I associate the EPAW just asked me to explain this. When you have wind in the system, your gas-fired and your other plant, it runs less efficiently. It doesn't feel comfortable, and you have to have trips to cut out when the voltage gets too high with gusts of wind. And it makes, as a result, this conventional plant needs more frequent repair, and all these bills are foisted on us. And it has been compared to driving your car. If you drive your car on a motorway, you get maximum efficiency at about 60 miles per hour, we'll say. Just drive it along under constant load. On the other hand, if you drive it in a city, you go over here, up here, stop at lights, down here, stop at lights, over here, stop at pedestrian crossing, over here, stop at lights, over here, stop at lights, down here, stop at pedestrian crossing, over here, stop at pedestrian crossing, and down here. So your car is not as efficient. It's stopping and starting. I think you understand that. And my association, which comprises several engineers, have pointed out that point, that it's completely ridiculous to say that you can just feed wind power into a conventional system and there's no price to be paid. There is a huge price to be paid. So the problem is that as you're running your wind, you are duplicating that. You're duplicating it with conventional plant or imported nuclear fuel or whatever, and this problem gets worse as you increase the penetration. So that's basically now all that I can tell you on this thing of wind, and maybe it's a little bit of a help. Some of this is hotly disputed, but we'll see later where the evidence is that this is the case, that they're unable to actually make good use of wind power. And I couldn't do it in the 1960s, and no one has ever managed to do. Wind power is around since energy generation and electricity generation began in the 1900s, and yet it was tried and tried and tried. And just like my own wind turbine, it was a great novelty, it was great fun, great crack, but it didn't work, and it won't work now. Thank you very much. We'll see you back shortly.